By the way,
Did you call it?
no, it was the point where I hopped to I knew it was very well difficult. So when you look at that, very well. Yeah, it's not go. Always be.
Yeah. Okay. Yeah. So as I said, I think even if you have the stochastic, even if you have the deterministic preferences, you can get stochastic approximations to it. And secondly, the assumption that the deterministic preferences were in PHTN format is an inductive bias. The first paper sort of makes it very clear. The second paper doesn't say anything, right? And it's just assuming that I have enough pairwise comparisons and I'll somehow figure out some reward function that captures the preferences underlying. Any other points? Yes, go ahead.
I just didn't really understand why in the second paper with the deep learning, why the synthetic oracle example performs so much worse than the regular reinforcement learning example in some cases and better in other cases. They seem very similar, as it's sort of just asking, like, are these two trajectories, is one better corresponding to the reward function that's being provided by the oracle versus just comparing the actions with the reward function through regular RL?
I don't have a good answer. Do you have any idea?
So in the deep learning paper, they had graphs for like the results. In the regular reinforcement learning example, in some cases performed a lot better than the example with the synthetic oracle, which was just provided with.
I understand synthetic oracle giving the response.
Yeah. So there was a line on the graph that just said RL. That was.
I think that's underlying reward function.
Yeah. So you can take into account any preferences whatsoever.
So an oracle is using that reward function to come up with 0-1 responses. And then you have a plot saying, okay, you use these binary responses, what happens? And then what if you had access directly to that reward function, underlying reward function, and you use something like whatever, CPU or whatever they use to train it, then what happens? So that's basically they're trying to give an upper bound. It's not really an upper bound, but they're trying to give a baseline. This is the best.
So what the RL that you're saying is essentially the one that already has the reward built in.
The underlying reward.
It's been given. So in the PHTN example, the humans are using PHTNs and you're trying to reconstruct the PHTNs. And then you're trying to see how good your reconstructed PHTNs are with respect to the original PHTNs. Now, if you just take the original PHTNs and generate the behavior and reconstruct PHTNs and generate the behavior and see the distributional difference, that is what it's saying. So if the reconstruction is not good enough, in the case of PHTNs, at least we are assuming there is a representational bias that original thing was an PHTN. In this case, you're assuming that there is a reward function. That's it. Over the states, there is some reward function. And the oracle is using that reward function to generate the pairwise comparisons. And all it's saying is that it's not good enough. Like clearly, you cannot completely reconstruct the reward function unless you do humongous number of pairwise comparisons. Yeah. Yes.
I think that there were cases where the oracle was actually outperforming the reward function itself, though, which was interesting to me.
Does not particularly make sense. In that
No,
case.
but actually, it was also pointed on a review for the same paper, some other things. But it so happens because, well, I tried to reason right now. It so happens because if you directly train an RLA, even on the underlying reward, there's this whole theory about potential shaped reward functions and why exploration is needed. Even if you have access to underlying rewards, right? And if your exploration is very poor, like your performance might not be as good, right? But in the other case, like the planet or this paper, they incentivize exploration a lot, and they incentivize a lot of that before even things start. Like I think a variance of that. So I think most of this boils down to the fact that base RL plus even with the underlying reward function, they don't have explicit rewards for exploration, or they don't do that as well. So even if you have access to the good reward function, you can't really use it that way.
Yeah. So
So it's added exploration, then it's not
Yeah.
something about.
So that
the way
is
that the
being seen like in the next iteration of works by other authors. It was seen that if you just do that, even if some of my experiments have shown that this is possible. That
Okay,
even
thank
if
you.
you have Oracle, but you don't do exploration as well.
So in the context of exploration, by the way, here is a way of thinking about it. Remember that if you have a reward, right? If you reward shape the reward such that you will actually get to the optimal policy much faster, right? That's like basically adding an H star on top of the MVP, right? Just because you happen to know the true reward function doesn't necessarily mean that. It only means that at the infinite number of infinite training, you are going to basically converge to the optimal values. Okay, so here is it. So there's so many things that are kind of moving parts here. So in the Oracle case, there is a question of how many questions you are asking the Oracle. And having decided, suppose I'm only going to ask 10,000 questions. After you ask 10,000 pairwise comparative questions, you don't have to stop. You can still, using that particular reward function, whatever approximation of the reward function you have, you can continue iterating until you reach convergence. You see what I'm saying? It can take time. How much time you will take, having been given a true reward function, how much time you will take to converge depends on essentially how regularized the reward function is. So it's like H star should be there instead of just R.
Yeah.
You see what I'm saying? And normally in the reward shaping, as I said, H star is actually the world's best reward shape. Okay. So in reward shaping, somebody else just puts an extra constraint. So basically make something like a sparse reward. Many of these cases, these are sparse rewards, these are myopic rewards. And for you to be able to realize that, for you to actually converge with those sparse myopic rewards, you will need a lot more exploration, a lot more essentially. If you think in terms of just MDP, like you need a lot more iterations.
Yeah.
Okay. Any other? Okay, so the kind of editorial comments I wanted to mention about this basically is, something that I did mention already, but I just want to make sure, that you remember this, that so the two papers talk about very different kinds of problems, and it's something that you want to understand. Okay, they all use the word references, and I can't stop what you like. You like deep reinforcement running, fine, but the problems that they are using essentially in one case, like the gate, the kind of gate, and which one, can you do more graceful gate? Okay, and in fact, that's the reason why one big issue is preferences are over trajectories. And they're showing the trajectories by showing video excerpts to humans. There are two huge issues there. One is your domain amenable, is your task amenable to short video snippets? You understand what I'm saying? Like, for example, I have a preference over how this country should go, let's say, and you're trying to figure out my preferences, right? How exactly are you going to show me two United States videos? I say, which video do you like? Those videos are extremely hard to produce compared to I'm walking like this versus walking like this. Which one do you like? Because all I'm doing is actual video in front of you. Whereas I'm talking about how I want the United States to evolve, there is nothing that I'm showing in front of you. I'm describing in symbolic terms approximately and trying to paint a picture in your head. And so it becomes very hard to show two pairwise video excerpts to people and say, hey, which one do you like? In fact, when you ask people, you ask symbolic descriptions. Would you like a world where everybody has free money and people are just kind of, maybe possibly taking advantage of your hard work and getting freeloading versus a world where everybody is meritocratic? Those are the kind of questions you ask. I just said English. Depending on your biases, you already imagined some videos in your head. I didn't show you videos. You understand what I'm saying? This is, and so I don't even need to go to the United States aspect. I can just say, would you like the world where the blocks are such that always the colored blocks, when the blocks are stacked, always there is like a run of color, that is all green followed by all yellow followed by all red, versus do you not care whether it is mixed up? Suppose my actual preference is I want all the colors to be in a run. How many pairwise comparisons are you going to be able to show even of blocks world, which by the way is not working? You understand what I'm saying? And that becomes extremely hard. And so, not surprisingly, the closest deep learning, deep RL folks have come to for anything really sequential but not continuous domain is things like Atari games. And these ideas, as far as we know right now, these pairwise comparison ideas don't work in even Atari games. Forget about the United States. Okay, that's one question. The other question is, who is the human who is ready to give you pairwise comparisons of the order of, thousands or millions? Remember, if it requires thousands of comparisons on how to walk, it might require a lot more number of comparisons on more complex domains. And none of you question, where is this oracle coming from? We have an oracle, let's run with it. That makes you engineers, because you really don't care about humans. Humans are an obstacle. Let's just let human be a tuple, 5 tuple. Right? And so you have to understand that is something that you have to realize. In fact, I think I mentioned this to you in the previous class, that people in the AI safety who want to save people from AI also want to say, what's the best way to simulate humans? So let's just call GPTs. This is our best ideas. You understand what I'm saying? So you do have to, you can do it. You can write that paper, but you have to understand what the limitations are, because this is a class. This is not, one way or the other. So you need to understand what the limitations are for those. And then the other side. So this is one type. The other type is explicit knowledge tasks. The PhDs were mostly the explicit knowledge tasks. Okay. And there, it's not because pairwise comparisons won't work. It would be infeasible. The number of pairwise comparisons that you will have to show, and actually making the videos of that, and actually willing people to sit down and see these two videos. Believe me, if you were to be able to generate videos of how different decisions will change the evolution of US, you can make those videos and show it to people, and you do it in a systematic, unbiased way. And if the people aren't bored to death because there are too many of these videos to see, you can get their preferences. Because the videos are hard to make, people with ulterior motives make one video and show that. So for example, if I'm very worried about autonomous weapons and I really believe everybody should stop everything else other than only care about autonomous weapons, there is this video that I should, does anybody remember the name of that video? The one that Stuart Russell figures in?
Killer drones.
Killer drones. So he made an actual scenario video. It's highly loaded because it is just their particular, it's not like they said, all possible systematic decisions that you can make on all different worlds and say which one you want. He said, well, if you don't like AI safety, this is what will happen. Do you like this? And there you're all getting all killed by random drones in the classroom. He said, oh, apparently not, I won't like it. That's not preference learning, that is preference imposition. And most of the world imposes preferences, including recommendation systems, as I mentioned earlier, because it's harder to learn your preferences than to tell you what your preferences should
Oh, okay, sorry, wrong name, Slaughterbots.
Slaughterbots, yeah, Slaughterbots. Yeah. I mean, what part of Slaughterbots doesn't give away whether it is a impartial video? You understand what I'm saying? I mean, all the campaign ads, by the way, are trying to understand your preferences, are trying to tell you what your preferences should be. They are the pairwise comparisons. They do it on the focus groups, and then they realize that the focus group people's minds can be easily messed with, and they're showing it to you too on the TV. That's what pairwise comparisons would be like. It's not even pairwise. It is like you show one extreme case of what happens if you make the mistake of selecting this other guy. And then you say, I mean, I really want to do that. Okay. But I mean, the point I want to understand is making videos, when I tell you a word, you imagine a video, which is like very loosely specified. You don't actually understand all the details, but you kind of think that you understood the word. And then you might have preferences over it. But I have to tell you that symbolically. I can't actually show you the video. Whereas for the walking, I don't know, I actually can show you the video, walking. It's very easy. And I can take a 3 millisecond clip and then say which one do you like. And it's kind of very important to understand that there are two very different extremes. This is one side and this is the more explicit knowledge type side. The other thing, so actually, as I said, there was a whole entire tweet thread that essentially was this. It's just like my lecture for today almost. Okay. So I'll just read it at least to you that, as I said, so even for the gait locomotion task, the sample complexity in terms of number of queries made to the human is so very egregiously bad that there is really a cottage industry of writing follow-on papers showing that you can improve whatever is happening right now. Because there's just extremely high number of samples that you need to do. And then most of this work emphasizes on human preferences, but the papers replace humans with simulators, or what you guys call oracles. The question you had was, why the heck is Oracle coming? It is, it's not why the heck is Oracle coming, it is why is Oracle wanting to do it better than the But so that's the interesting part. So you do have to understand where these human simulators are coming from. And then using human simulators, as I mentioned one time, is kind of like using world simulators, except on the human side. And so you can basically, you don't have to deal with how reasonable it is to actually ask these many questions. By the way, even with this, making the video is still hard for long horizon. Explicit knowledge tasks is basically impossible. Because you are not showing videos, as I said, think about those ads, etc. So they're like, for that type of approaches, people basically use qualify. And the question winds up being which type of task you're more interested in. If you're interested in the task knowledge, micro horizon task, it makes sense to actually look at these particular approaches. Yes.
So wouldn't it change a lot about like how like a human might prefer one trajectory over another, given like how the video is like cut? Like if you don't have like knowledge of like steps of like hierarchy or whatever, like this is one step of it. If you just take like part of it, like I don't know if you're like training an AI to throw a baseball, that's like winding up versus like winding up a little less, it can be kind of hard to tell, like because you're only seeing part of it.
It's basically the famous horizon effect, and essentially it's interesting, everything is connected, right? So this is basically talked about in the game theory classes, right? About the horizon effect is an effect that comes in the game theory, where the example you use is the allies are trying to figure out their preferences. as to whether they would prefer to wage a war on Hitler or it's not worth doing the war right now. So they had to simulate what happens to the world with all the unknowns. You know, what happens to the world if they do war versus they don't do war. And some things are easier to imagine. Oh, war, lots and lots of people will be dead and the papers will be full of casualties. Not war. Yes, Hitler might continue, taking over the entire world, but maybe he will just stop after Czechoslovakia. Okay, Poland, maybe Czechoslovakia and Poland, not more than that. The point is, I can always tell you the video. I can imagine the video to the right level so that you would follow my particular preferences. And in game theoretic terms, essentially all that says is in any limited horizon, this is actually a very interesting point you bring up. In any limited horizon search, the inevitable can always be pushed beyond the horizon. See what I'm saying? That's why horizon effect is never, you can never actually get out of the horizon effect. So the answer for this actually is again a very interesting question about the video length. So what is the length of the videos these guys are showing in the Temporal paper?
5 seconds.
5 seconds. Okay, so do you really believe that all your preferences about walk are in terms of 5-second intervals? What if the people who can walk like this are for 5 seconds, as the 73rd second will have dizziness and fall down? Do you understand what I'm saying? So I show you two 73-second videos. Then you say, I know, I like the beginning part of this guy, but he's dying in the end. This other guy is looking boring, but at least he's not dying by 73rd second. So your true preference is actually the boring one, but you thought your preference was the original. You can avoid this by not even talking about 73-second videos, but infinitely long trajectories. Do you see what I'm saying? Infinitely long trajectories until the trajectory ends in a dead state, basically indefinite horizon trajectories. If I do that and I show you two infinitely long trajectories and say, which one do you like, then I'll understand your preference. You're saying that's too hard? Yeah, it is hard. It is hard to understand what people want. In fact, we are a living proof that we don't know what we want. The entire history is a proof of we don't know what we want, because our imagination itself is constrained. And we will imagine, oh, something seems to work well, but you only consider a certain horizon. And then until something else becomes immediate, you don't realize it's the problem. So not only is it hard to make the videos, in fact, these videos should be infinitely long. And they should consider all possible eventualities. So that's sort of connected to the point you're making. Yes.
So even if the videos are infinitely long and you get a very high quality single preference ordering between the two videos, you still are spending a lot of time per comparison. So you end up having fewer comparisons at the end.
I agree.
Right?
Yeah.
So,
but I mean, you're teaching to a choir of one.
Yeah.
Because look at the rest of them, yourself included. They actually, I mean, it's not surprising. I mean, one of the interesting things is popular things are popular because they're popular. It's like a recursive definition, right? And so the question is, why isn't this a problem when you basically, more of you generally were more positively impressed just by reading your, reviews with the deep reinforcement learning based trajectory comparisons than the PhD one, right? I had many of them today, right? And so the question is, you are essentially ignoring some of these problems. The cost of comparisons is hard, but if you don't actually have people, and if you put in Oracle, the question is, getting this Oracle. If you know the Oracle, why can't you just put it into the Oracle? Why even ask the Oracle? In fact, one of the biggest points that Minsky said is all of intelligence is shifting test part of generate, test, debug into generate part. The test normally in the preference learning is the human who knows and you don't know. But you say you know the oracle who knows all the preferences. And this oracle is a computational oracle. It's just like simulated RL with simulator is not RL. And RL with human simulators is not real preference learning either. Because if you had a simulator for the human, that means you knew what humans like. Unless there is some kind of a thing like you think that a GPT-3 will know. And GPT-3 was trained on the world's entire data, and so that's why it knows. So I may not know exactly how it knows, but I just believe that. So in general, if it is a computational oracle, then problems that you have become computational problems as against cognitive load problems. Okay, that's why I said basically human simulators stop. I mean, having simulators for humans stop the death of humans who might be bored to death trying to do these pairwise comparisons for all and sundry systems. Okay, so that's yes.
I mean, okay, so from a more like practical point of view, it's very difficult to benchmark your results against other results if you don't have some standardized way of testing them, right? And I suppose the Oracle is the most obvious solution to a standardized test.
Yeah, but I mean, the point is that there's a difference between doing the Oracle only to improve standardized testing versus you believing that when you are ready to put it in the real world to learn the real humans' preferences, the same ideas will work. Because the orders matter. If you reduce the number of pairwise comparisons for a small walking domain from multi-thousands to a couple of thousand less, that's not good. That's just not good enough. Okay. And in fact, it makes a lot more sense that it is a simulator in those cases because the number of calls can matter. I mean, again, my point is I'm mostly pushing this side because essentially these are the things that you don't necessarily see it yourself. So it might be worthwhile. Having heard this, you would say, yeah, I still would prefer doing trajectory comparisons. That's completely fine. So the other thing that I was saying in this part, which sort of is that so this is the second big part, which is the bigger problem is that these papers are written, the one I had in mind. When I say these papers, I had Cristiano paper in mind. Okay, the one that I made you read. Is written as if they would also make sense for long horizon tasks. And much of what I was discussing here is they don't actually. Who is making these videos for you? How long are the videos supposed to be? Who is sitting there and watching these videos? You see what I'm saying? If I actually try to get your preference on your entire life, you don't have time to look at your video of your entire life. I mean, there's this old statement saying that if you recorded your entire life, you won't have time to watch it. Just tautology. This is now extended into you recorded all possible lives, and you are trying to compare the possible lives to figure out which one would you rather have. You won't have time to watch it. Right? So that's sort of a thing to keep in mind. And then, again, it's like, this is like videos, length of videos, number of who makes them, how many comparisons. These are at least the minimal number of things you need to ask. Okay. And then, so really, do we really believe that a trajectory CPET comparison scales from locomotion to a ballet level? Forget about how US as a state evolves, right? Just ballet. I can show you 5 millisecond snippets of ballets, right? And can I understand your ballet, preferences? Of course not. You can have both micro and macro level preferences. You can actually have hierarchical structure to your preferences too. And you need to essentially see them at different levels of resolution. And the way I'm going, so how exactly are you making this hierarchical resolution ballet? Okay, and it won't just be taking every millionth frame and showing. That doesn't work, because that would be just basically useless. Summarizing long horizon space-time tubes is hard. I would argue that actually we came up with language just for that. Okay. So our preferences for ballets seem to be based off of a more abstract level than fine locomotion snippets. More often than not, preferences are expressed in quasi-symbolic forms. I prefer more athletic ballets. I mentioned this last week, that's our thing. Such preference abstraction holds for all long horizon tasks. So it may be possible to learn these. The question, of course, is how do you learn these multi-abstractions? And if you are thinking of learning these multiple abstractions from sensory levels to symbolic abstraction, which is what we were talking last class, there's an added question now that the abstractions you learn should make sense to human, not just be computationally advantageous to the machine. Because they should somehow be able to humans should be able to make sense of them and then give you their preferences. You can't just say, I came up with this abstraction because it's faster for me to work with. So that's basically the things that, and so at some point, I don't see how you can get away without having some kind of a symbolic that people understand. And so, in fact, there is a paper that is Lynn here? Maybe Lynn isn't here, but Karthik is here. Lynn and Karthik are involved in this work. That's sort of, basically what they're looking at is middle type of tasks, which essentially you want to provide preferences, not just by doing pairwise comparisons, but by giving symbolic descriptions, saying walk faster, walk slower. That's what ballet dancers get lessons. Some parts they'll show, some parts they say, and it's like a multi-modal interface, right? And so the question is, can you support relative attributes? There is this idea called relative attributes. Attribute normally is an attribute with a different set of values. A relative attribute is with respect to the current state, faster versus slower, bigger versus smaller, darker versus less dark. Those are all relative attributes. And if I were to then get my suggestions in terms of these relative attributes, that's the workshop that they have this paper on. If you get these suggestions on relative attributes, how can I use them to improve the number of pairwise comparisons, which sort of tracks both words. On one hand, you want to still do, sort of your if your RL agent is still pixel based, you may want to do this. You may want to do pairwise comparisons, but you want to not force people to look at pairs because they only have limited amount of time. So they're likely to see go faster versus go slower. And you should be able to make that, convert that into, operationalize that into the behaviors that you show to the humans. Okay, so this is like a small example of the kind of thing I hope will, basically that's the kind of thing that works for us. We kind of use, we have tacit, we have explicit knowledge. We have symbols, we have just demonstrations. We combine with. And that's something that's worthwhile. Okay, and so they have nice results and so on and so forth. So you can look at that. I think it's going to be coming on archive. Does it come on archive? Yeah, I can send you this. Okay, that's the thing that I want you to think of. And then I want to move to something different, which is, okay, here. I don't know why this comes so big. So this is the second part, which is making plans for humans that take their limitations into account. So one interesting question is this. That's a nice way to drink, right? It looks like a jug. There is a handle, there is a spout. Why don't you see these kinds of jugs in the world? It works, yeah.
Because you will end up like pouring.
Exactly. So who are you thinking will use this? Humans have to use this. You understand what I'm saying? Humans have to use this, And if you give this to humans, then they'll essentially will hold it and try to pour it like this, and it will fall on. Okay, another version of this is there is a door, a glass door, and you can't tell whether you're supposed to push or pull, right? And so then basically just they'll write in like small letters downstairs, push, and the other side pull, and people keep getting into confusion, and you'll wonder what's happening. And it's because you essentially did not take into account the fact that humans have multiple things they could do when they go to a door. They could either do pull or a push. And you should make the affordance on the door be such that some of the choices will just go away. The best designed doors that require push will not have a thing to hold on to. Having a thing to hold on to and say push is dumb. Because if there's a thing to hold on, I can either push it or pull it. Whereas if I just put a metal plate that you have seen, lots of good places where people are not jumping into each other, they put a metal plate, you can't pull the thing with the metal plate. You can only push. This is basically Don Norman. You guys should read this book actually. These are just two of the many examples of the psychology of everyday things that we designed for ourselves. And a classic, and this is kind of connected to things like HCI2 and the Brickyard Bozo elevators. The Brickyard Bozo elevators, somebody decided the important thing is to make sure that tell people only when they need to know whether the elevator is going up in the, if the elevator door opens, I don't know, those of you who ever came to Brickyard, the elevator door opens, right? And you want it to go up, and you don't know whether it's supposed to be going up or not. It's not saying anything because its argument is, look, you want it to go up. If it was going up, I would have told you it is going up. If I don't say anything, you should assume that it's not going your way. So what happens? We become better friends because everybody asks, are you going up? Are you going up? Are you going up? Are you going down? It's like unnecessary conversation. Have you seen this? This is the definition of bad design. This basically ignores the fact that people would like to know which side it is going rather than assume that I will be told if it is going my way. So they saved one light and made us all talk to each other, which probably is not a bad idea, but so much unnecessary conversation, right? So the question is, if I'm making plans, these are objects. If I'm making plans for people to actually execute. The best was when before the Google Maps, you had to call your friend and give them verbal directions as to how to come to your place. Probably you guys weren't born before Google Maps, so you don't understand this problem. But one of the things is that you have to understand that people need lots of extra information, which is like for example, say, if you have started seeing the big McDonald's, you have gone too far. Have you ever heard of these kinds of directions? If I say, when you have gone so far, too far, because people do go too far and they just keep going further if you don't tell them this. So here is an example of a plan which has this extra information thrown in mostly to make sure that it handles the limitations of people. Right? This also went under the name of human factors, human computer interaction, etc. So my question is, what would look like the psychology of everyday plans? If the plans that people have to execute, let's say that machine came up with a plan for you to execute. So instead of you calling your friend to give the directions, the machine called your friend to give the directions. Now notice that this problem has completely been removed right now because the Google Maps sits on your dashboard and keeps on yapping the whole time. Right? And so you say, you got too far, go back, and then or change, if you are like, for example, in fact, I don't know if those of you noticed that Google Maps nowadays says, in front of you, there is a traffic jam, but this is still the best path. Why does it have to say, why can't we just assume Google knows what Google does? Because we don't believe. We should be told that it somehow realized what we have realized, and that even though it is traffic, in fact, most people, especially I think men, see a traffic jam, they just go off to some Pozo street and spend 3, 4, 5 years, just because they at least avoided the traffic jam. And even with Google telling me I do it, by the way, the other day I did, I said, how the heck do Google know I can go off myself? And then you waste your time. It takes into account the human limitations in making plans that way. So the question would be, I thought it might be useful to think about that and making plans for humans that take their limitations into account. So we have a newly minted doctor right here, Dr. Sriram Gopalakrishnan, whose dissertation was this, essentially. So I asked him to do one part of it, essentially for you. And so that would also be a good way of ragging a newly minted doctor. And then I'll come back and do temporal plan. Okay, that's what we do. Just want to use the sharper form. That's simpler for you. What? Oh, maybe I can put it on there.
Speaking of simple design, I should have stayed in school.
So you see that these are more modern slides with like the 9 by whatever 16 ratio. Okay.
See,
I'm right here, but
he's had it with all of you. So what we're going to talk about now for a bit is when you're giving plans or policies for humans to execute, one thing we need to take into consideration is that people have cognitive limits. We may not be able to infer where we are at any given point or the exact state of the world perfectly. Given our finite attention spans and inferential capabilities, we may mistake one state for another. So if we give a plan for human to execute that considers how we make mistakes, we can actually get a better outcome than perhaps giving an optimal plan that the human is going to mess up during execution. So to build some intuition, let's consider this trivial case on the right. The arrows seem to be a little messed up, but let me give you the gist of what it is. On the top set above the little checkered flag, there is a more convoluted set of directions to get to a goal state from any position. On the bottom is a much more simple set of directions. Just keep going down and then turn left. So that should give you a sense of a general intuition of what a simpler plan is versus perhaps a more optimal plan that maybe if you follow those convoluted directions, you may avoid the most amount of traffic, but it's a lot harder to follow and you may end up taking a wrong turn. So with that in mind, this may be a little heavy in terms of I won't go into too much of the math, but if we consider that we have a model of how humans confuse two states, that's this little phi symbol in there. And if I have a sense of how the human is going to confuse state 1 with state 2, and if the actions are different between those two confusing states, then we're going to call that policy as more complex or more confusing than a policy that had the same action for the two states that are very similar to each other. So given this, how much of this do I want to go over with you? Let me perhaps give you a more intuitive example. Yeah, this one. To build a case, perhaps a real world case where it could be used. Let's consider a warehouse worker for a company like eBay or Amazon. They go through day in and day out, taking a set of products and putting it into a box. Now, which is the correct size box to put it into? Oftentimes, you're dealing with products of very different sizes, and they have to determine the exact right box to put it into. This is a very difficult problem. There's an entire problem called bin packing in computer science dedicated to it. And if you expect your warehouse worker to optimally pack products into the right size box, it's not going to work out. Instead, if you knew that your cost, the extra cost for using the largest box was just a fraction of a cent more than using the right size box, you can just tell them, put all of the orders in the bigger boxes and ship them. You'll actually end up getting more value over time because the human isn't wasting time taking the wrong actions or delaying their actions in order to choose what to do next. So this should give you a sense of why you want to trade off complexity and value. The optimal value or the optimal plan may be woefully suboptimal for a human to execute just because of our inference limitations. I may not be able to figure out exactly how to pack 3 products into a medium-sized box, even though it's possible, if you angle it just the right way and you place the tools in the right way. So this is a scenario where I hope you get a sense of why we need to consider limitations when coming up with plans for people to execute. With most of computer science techniques today, for robots, they're great. Robots can figure out exactly the state of the world. They're not as distracted as humans, and they're able to execute faithfully. With humans, we have finite attention spans. We have horrible memory. So even if I detect the state correctly, I may forget what the action is that I have to do here. So this is a lot of my work, is trying to figure out how we can convert knowledge about how we mess up states and compute policies for it. So what I assume here, don't worry about the equations, I'll make it a little simpler, is that if I'm confusing 2 states, there's a likelihood that I'll take what's called a null action, which is an action where I'm doing nothing. Our poor warehouse worker takes a set of products and spends some time staring around figuring out what box it is. If we change the execution dynamics, or rather how a plan is executed using this model, we can apply it onto existing methods for solving MDPs, or Markov decision processes, to come up with a plan. Another flavor of this very same problem considers an extra step. First, we talked about complexity and value. Simpler policy, better for the simpler human. The other question is, how does a human actually act when they're uncertain? They may not just be staring around. They may try and resolve uncertainty, or they may take actions to figure out where they are. These actions may have a cost. Now, if you don't factor this cost into your computation, you're once again going to end up with suboptimal plans where you thought they were optimal. And that's the second flavor of work here, where we consider how the human gets confused. So if, let's say, here's an interesting thought experiment. If I'm blindfolded, and this is a slightly annoying party game, your friends push you into a room blindfolded and ask you to figure out which state you're in. You may be able to touch a wooden table and you would infer one of 2 things. I'm either in a kitchen or in the living room. If I know that this is how a human infers states given the true state, I can come up with actions for them to take, saying, whether you're in the kitchen or in the living room, keep going straight. You should end up next to the piñata to whack. Whatever party game this is, let's imagine that that's the case. So what I'm trying to do here is figure out, based on how humans get confused, can we give them a policy so the action they take is going to allow them to make mistakes and get to the right answer or the right state either way. The math heavy part is not necessary right now, but the point I want to make is consider when you're dealing with people versus robots, what aspects of our inference limitations is important for the problem, and bake it into the problem setting. I think, Dr. Rao, this is the level at which I can present it here.
I think you can go through your formulation, they should be able to understand.
Okay.
You're reading Paul Christiano's paper, so I'm sure.
Fair enough. Then I will go over the formulation just a little bit. Let me see if I can move that video out of the way.
You can just push it off the screen. No. You're talking about this.
Yeah, the
video,
little
right?
thing.
Yeah.
So I'll go into a little bit of detail since Dr. Rao has a high esteem of, as you should always think better.
It's still the first day, so the PhD can still be taken back.
Well then, when the human is executing a plan or a policy, ideally we'd like to evaluate the human on all the possible plans and see which ones they execute the best, and then tell them use this plan all the time for, say, like packing. However, the space of possible plans may be huge. So we can't afford to evaluate a human on all possible plans. So what we focus instead on is the smaller task of state identification, meaning we just want to figure out how the human gets one part of the execution wrong, which is how do they mess up identifying the state? If we have that information, we can take care of figuring out what the plan is. And modeling that state identification error is what we do with these 4 terms. The first term, PC, is a probability of a human classifying one state, S1, given that the true state is S2. So this is how they're confusing things. The second term is the probability that a human is going to be uncertain over a subset of states. So they may finally decide that it's S1 given that it's S2, but before they made that decision, were they confused between it could be S1, S2, or S3? So getting the probability of a subset, like what's in their head before they decided. That's what PU tells us. These are simple probabilistic models. It's not complex cognitive architectures. Then if they are uncertain, what we'd like to know is how are they going to respond to that uncertainty? So there's a little bit of behavioral modeling here. Is our warehouse worker going to say, take some extra actions to figure out what the right box is? They may take the keyboard and put it next to a medium-sized box and ask, will this fit into this box? And use that to infer, is it really a set of products that goes into a medium or large box? So there's a bias likelihood where this is a very low self-esteem human who's always taking extra sensing actions. So in that case, that psi-naught term would be higher to model such a scenario. What psi-1 tells us is if they are uncertain, not just a bias term, how much more likely are they to take it? So in Amazon, they're famous for saying, finish as many products as possible. This term may actually be very low because of the pressure to complete orders. They don't have the luxury of trying and figuring out which is the perfect size box. They may just throw it into a box anyway. So in this way, we model a very finite subset of the human's behavior, just as much as is needed for us to figure out what plan to give them. So how do these terms come together? We first want to consider or determine the likelihood of a human taking this A+ action. What A+ action is, extra actions. It's not part of the plan we told them to do. They're just trying to take these actions to figure out where they are in the world. And they would take this action for a given policy we give them, pi d, which is a deterministic policy, based on this bias likelihood. Let's call it their self-esteem ability, where the higher this bias likelihood, the more likely they'll take it, regardless of uncertainty. And the other part of the term is the second line here, which tells us If the human is uncertain between a set of possible states, this is probability of uncertainty, PU, and in those subset of states, the policy is different, then they are more likely to take actions to resolve that uncertainty. So it's a fairly straightforward decomposition of how you compute the probability of them taking this action that's in addition to the domain actions of packing. Now, how often do they actually take a policy action, meaning our warehouse worker is not just trying to figure out where it goes, puts it into a box? That likelihood is given by this equation, where I'm going to take an action based on how I'm confusing states. If I think, if that human confuses state Si for the true state S, then they will take the policy we told them to for that state, not what the real world is. And so this is how we model the dynamics of how a human is going to act if you give them a plan. With this information, we can then apply it to some simple policy iteration, a policy iteration approach to computing the policy, where we start with a random policy, a random plan, and then make changes to this plan and see how the human would behave based on this model we described earlier. And if that behavior is better, we get better value for a particular plan, we'll continue that search of just tweaking each state. It's an expensive process, but it is, and it's also a heuristic process. It's not guaranteed to give you the optimal value, but it can handle larger state spaces better than the second method we have, which is a search method to figure out the optimal policy. And in this way, we were able to see that both the heuristic and the optimal method does give you better policies than, say, ignoring the human behavior altogether. So I would like to stop at that point, Dr. Rao.
Okay.
Are there any questions people have?
Please.
So the human's model of the robot also changes based off of whether the robot gives a correct response or not. So I would imagine if you're an Amazon worker and the robot says, use a big box, and the big box turns out to be small and you need an extra large box, the human's going to trust the robot less.
So this is assuming in this work over here, I haven't yet considered an extra robot teammate, but we can extend it very simply. Let's say there was a robot teammate next to the human packing, and the robot teammate sees it and says, human, use a medium box. I don't know why the robot's ordering the human here, but let's say they're doing that. Not only could the robot be wrong, but even if the robot told the human the right answer and the human doesn't know how to do it, they may think the robot is wrong anyway. So that's another level or dimension where in teaming, you need to consider the mental models or abilities of both agents. So when the robot says, put in the medium box, if the robot knew that the human might not be able to do the bin packing properly, it might have given the human a different action.
So just one thing, just make sure that you are the same mental model in this particular case. The work that he's describing, the plan is for the human workers to put into big versus small boxes. In Amazon, by the way, it's the people who put things into boxes. The robots only bring it to people. We still don't, they still don't have the technology as yet to put things into the boxes. Okay. So there is actually, there is no collaboration between humans and robots here. The bigger point here is the policy is made for the humans. And it should be easier for them to. So there's no question of they're not trusting the robot. It's like
they're more like trusting the policy that's given to the human by the AI. I think that's how it creates the question.
Okay, yeah. So I think basically, I think they're just employees. They're following the policy. It's easier for them to follow than that's the point. I mean, you're saying, yes, it is easy for me to follow, but Jeff Bezos may have less money because of my action. There could be such human workers, I think, in which case your point will be better. But most people would rather that, okay, it's easier to handle. Any other questions? Okay, then we will take a 15-minute break and then we'll come back and have any more questions we think about, or we'll go into the temporal plan, which is like maybe next.
I still get to keep my PhD.
Yeah. Just 1 second. Yeah.
Yeah. It's missing. Mine did that too. And let me see if I can find it. This machine actually has a disturbing margin. Yeah. No, that's nothing.
Oh, I can do that. Okay. So yeah, we're going to shift into metric temporal planning. But before going there, are there any further questions on reference learning or anything else that we discussed today? But in general, keep in mind that there was a side discussion that somebody was asking, which is even if you somehow manage to learn humanities preferences, your preferences are not exactly the same as the humanities preferences. If all of us had the same exact set of preferences, then we shouldn't have any wars, we shouldn't have any problems whatsoever, right? So clearly we all have different preferences. I mean, and so really the question is, it's not even that, I need like 3 million pairwise comparisons, and since individual humans are hard to get, we'll just go to Tucker's and then shift it to each person does like 5 or so there'll be tons and tons of workers. But that's actually kind of combining lots and lots of different people's individualized preferences. You see what I'm saying? I mean, and certainly the preference of whoever the guy running North Korea is different from the preference of the guy who's running US. Right? And it turns out that if we're all Turkers, then 5 of the preferences would come from him and 5 of the preferences would come from Biden, and you're mixing all of them in essence. Okay. So in general, in the worst case, actually, you have to get all these 3 million from the individual user that you're trying to help. And you want to do it actually unobtrusively, if at all possible. But most of the work that you looked at essentially tries to do it by direct asking questions and pairwise comparisons. So the hope is that if you learn some kind of a macro aggregate preferences for the entire humanity, that may not correspond to any single individual's preferences, and yet if you start with that as the background knowledge, it might be easier to go from there and ask fewer questions to human, it's a specific human you have in mind, to try to customize the preferences that you learn for all the. That's sort of the hope that people have. But all of this is bleeding edge. Nobody really knows whether this can be done. As I said, the best example that was kind of breathtakingly egregious to me was, hey, let's just use GPT-3 as human preferences. In some sense, it's true, right? Because any random people wrote anything that sort of, is kind of part of the mix. Okay. But so you have to keep that in mind. And the other thing, of course, is it's very important to remember that it's infinitely easier to make up human preferences and find them. And as I said, there's a Heisenberg kind of an aspect to this too. You can ask questions in such a way that actually makes people have preferences that they think that they didn't know they had. Okay, and so in fact, in half of the time, in all of the recommendation systems, they essentially make up your preferences. You don't realize it. You just think, I mean, that's probably what I wanted. I mean, so suddenly, why is this on my timeline? Maybe I liked it. That's why it is there. So, and in fact, you can actually ask all sorts of interesting. There's just equal amount of adversarial AI research that can be done here, which is think in terms of the pairwise comparisons. What is the best pairs that you can show to the humans to make them, like you suppose, I mean, like the government might say you must ask people. So otherwise we won't give you like license to run this thing. So how do I ask the questions such that I will get the preference? I will get from them the preference I already decided for them. And companies are essentially doing this to some extent, right? So that's something that is what we're doing. So preference learning in general is a very interesting aspect. And I think somebody was thinking, I think Courtney, I think I made a note to your review that it looks as if the problems are the same in both the fundamental problems of preference learning are the same whether you do it in the PhD paper or the other one. Okay, the real question is what things are they pushing under the rug? Each of the papers, any paper in the world pushes something under the rug. The whole point of reading the paper is figuring out what did they push under the rug. As a chemist, just taking what they said at face value. Okay, so for example, I think the point that Courtney was making was in the preference learning, essentially paper, then we talk about in the PhD one, we talk specifically about the fact that the human behavior traces are not actually indicative of their preferences. By the way, it turns out this is very well known in the preference literature, but it's not known for AI people in general, okay? Because what you do may not be what you wanted to do. What you do is, that's why I use the word, I think that phrasing in that paper is, due to me, that preferences are obfuscated by feasibility constraints. Okay, so this is what I would like to do, but this is the only thing I'm able to do, so I'll do what I can do. That is still close enough to my preferences. And this happens like all the time. Okay, and it's not a problem just for the PhDs. It's also a problem for, in fact, one of the big issues in the context of the deep reinforcement and the thing is somebody is picking which pairs of trajectories to present to the human. That's basically, I was saying I can change the set of questions I ask so that I can get whatever answer I want to some extent. I mean, it's actually an adversarial preference learning, preference imposition problem. Okay, and it's not, and in fact, one of the funnier things is that especially if you are both learning the environment dynamics as well as the preferences at the same time, then it's actually possible that you only showed the behaviors that are feasible with respect to the environment dynamics you currently know. And that basically there are a lot more interesting things that people like, but you never showed them. Do you understand what I'm saying? Like, if I ask pairwise questions saying, what would you like, 50, hits with a whip or 49 whips with, hits with a whip? Clearly, it's a 49. So it looks like they like 49 whips, 49 whippings, right? But that's because I never asked you what would you like, 49 whippings or a ball of ice cream. I didn't ask, and so I would never know that you prefer a ball of ice cream to 49 whippings. And in fact, based on the questions, I can decide, for example, that you are a masochist. You like whippings. And then, so if I wanted to prove that that's the case, that's the questions that I'll ask. So you have to understand how much stuff is going under the even with millions of pairs of comparisons, there's still this problem of did you actually have any way of showing that first of all, were you able to show all the behaviors? And secondly, if you could, would you make sure that you had the coverage, the behaviors that you have shown? Yeah.
So something I've been thinking about was, for the deep learning paper, could you technically do what Danajar Hafner's paper did, which was learning the environment dynamics?
Fast, yeah.
But instead of learning the environment dynamics, what if you learn preferences?
No, that's the point. That's the whole discussion of last week, that if you do that, environment doesn't have a, humans do, right? In the sense, the point is in the preference learning, you don't want to say that we are completely ignoring humans. The whole name of the game is to say humans, we like humans, we're so good with humans, and then there's a human oracle. And the engineers will say, yeah, that's true. This is human paper, but we really are happy enough that there's an oracle. Okay, the moment you made it an oracle, then there's not much better. But because it's humans, then it does make a very big difference. Okay, so, yeah, there are connections. That's what that whole last week's class was sort of connected to the preference learning, and end of which I asked to read these two papers. Anyway, so I'm going to shift to metric temporal planning, which we started last class. And I just basically wanted to tell you that there are a whole bunch of things that you typically don't think of when you're thinking about handling time. This is deterministic planning. It's a different way of extending difficulty. Okay, you can, instead of instantaneous actions with stochastic dynamics, you have durative actions with the deterministic dynamics. And of course, you can also have durative actions with stochastic dynamics. Okay, but first at least understand how to do durative actions with deterministic dynamics. And you'll be surprised how many subtle points are there. There's a lot of work that's done in this area, but it typically doesn't get covered anymore these days because people are too busy thinking at the level of instantaneous actions. Okay, so it's worthwhile as a class to understand what you can do. And we went through these issues last class. Issues with time, how metric time allows you to talk about deadline goals, durative goals, and exogenous events, etc., and how the actions might be durations of actions themselves might be in a static or dynamic. That means the length of the action itself might be changing, and there may be actually stochastic dynamics there. In addition to stochastic dynamics of what the action does to the world, there may also be uncertainty as to how long the action is going to take. Right? This is, again, everything we say here, you will understand right away because you live this. Your life is actually temporal planning. It's not, instantaneous action planning. So it's very easy to understand, yeah, that makes sense. But so you have to ask yourself, how come you're not thinking about it? Why did you assume that all that is there is continuous dynamics, trajectories, like walking? These are also important. Actually, these are quite important in certain kinds of domains. So NASA, for example, cares mostly about temporal planning. Okay. So then what else did we say? So then I talked about this issue of make span, which is beginning to end, how long it takes, and how, for example, if you just add up the durations of the actions, then that is basically a strictly serial plan. If the make span, that is the time taken from the beginning of the execution of the plan to the end of the execution of the plan, is equal to the sum of all the durations of the actions, then that's a strictly serial plan. If it is even longer than the sum of the durations, then it's a serial plan with slack. That means once in a while, you're not doing any of the actions in the plan. If it is shorter, that basically means there is concurrency. That means some pair of actions are being done at the same time. Otherwise, you couldn't have a make span less than the total of the durations of the actions. Okay. And the question then is, in general, concurrent typically means two actions are being done in parallel. And so that connects to the parallelism of the actions that's connected to the partial order planning. In fact, at the end of the class, right? So he was asking, couldn't you do partial order planning with this? Actually, that's exactly what we'll talk about. Everybody first tried to do partial order planning for this. But then, one of the funny things is that while it is true that partial order planning will work for this, it's also the case that it's metric temporal and it has resources. And the question about resource constraints, whether or not the resource constraints are violated, is easier to check during planning if you have state information. Whereas if everything is up in the air with, like partial ordering, then you have to ask yourself, is there a cut set? Is there a potential state where the resource constraint will be violated? Okay, so it turns out that for a beginning, actually for the longest time in this area, people will just say, we'll just do partial order planning. And then basically people start thinking, can we do state space planning? And then one of my old students, I'll actually talk about this paper called SAPA, which is a planner, that was one of the planners, basically that showed that you can actually do state space planning to get temporal plans. And then we actually also showed that while that is the case, it turns out that when you do state space planning to do temporal plans, then you only solve temporal planning problems which could also have been solved if you didn't care about efficiency with strictly serial plans. The concurrency there was only to improve efficiency, not feasibility. Do you understand what I'm saying? There's a bunch of things, like for example, right? No courses that you are doing have to be concurrent. There's like really no reason. You can do your program of study by taking one course, one semester, next course, next semester, next course, next semester. If you have enough money to pay the tuition, we actually would like your money. And, and it would be good. You learn a lot more. You're doing concurrency for random efficiency reasons, which is why you don't get anything. You have 18 courses per semester. What can go wrong? What can go wrong is you don't get any of them. But that's, you feel good that I efficiently used my money. Okay. So course programming is a classic example of concurrent courses that could actually have been solved with a serial. You understand what I'm saying? And so if you could generate a serial plan and then later on make it parallel. So in fact, the true dependencies in courses are the prerequisite dependencies. So you have to go and beg and basically plead with the instructor, can I take the prerequisite course along with your course? Things of that kind, which actually doesn't make sense, but we might let you violate it at that time. But those are the real constraints. The constraint of I must do these two courses in parallel, that doesn't exist. And yet all your courses of program of study is concurrent. You are taking concurrently multiple courses. And it turns out that it's a very important difference. And the state space planning approaches for temporal planning can generate plans for all problems which do not require concurrency. Require concurrency means that without concurrency, there is no solution. Requirement, necessity versus luxury. Okay, so doing MS program of study, you can do it sequentially. There's no necessity to do things parallel. If on the other hand, we come up with two courses such that they really have to be done in the same semester, and we make it clear to you that if you aren't taking these two courses at the same semester, you won't get credit for either of them. That would be a strictly required concurrency scenario. And it turns out that problems like that exist lots of times in temporal planning, and state space planners, which you can generalize, it's a cute way to generalize state space planners, it turns out, they basically almost act as if they will solve all the problems except the ones they don't solve are the ones which actually require concurrency. And the interesting part of this that we'll get through hopefully is to see that as an entire community was smitten with state space planners, we were writing the state space planners ourselves. And then at some point of time, we actually wrote a paper. I mean, this one I know well because we were involved in the whole thing, that we wrote a paper showing that there were actually benchmark domains for temporal planning. And planners were winning these benchmark domain-based competitions, temporal planners. And none of those temporal planners can actually solve required concurrency problems. Then why are they winning? Because the benchmark doesn't have required concurrency problems. They just made up a bunch of problems like MS program of study, where all that mattered was parallelism. So it was a collective. Test guy didn't know, training guy didn't know. So all of us were, test guy didn't know, exam taker didn't know, and so all of us were happy. And then basically we showed that in fact this set of problems can't be solved, and that you do essentially have to bite the bullet and go back to partial order planning to get the completeness. Okay, so that's the the thing that we'll try to get across with some more details. So again, as I said, issues with the resources, one big thing to remember is that resource constraints are easier to check if you have a state information. Because in a given state, do I have enough chairs to sit all the people, for example? Whereas if things are parallel, then it depends on whether or not you have enough resources, depends on the actual order in which the actions are done. And so it becomes harder to check. This is the usual problem with least commitment planning. In the least commitment planning, if you don't make any commitments, then you have lots and lots of freedom as to what you can do next. But on the other hand, you also have no idea what kinds of where you are. If you have a partial plan where everything is up in the air and you're not actually kind of making any commitments to start, okay, my travel for the holiday starts at this point of time, my study for this exam starts at this point of time. If you don't make any of those constraints, you leave everything in parallel, and then you have a harder time figuring out, do I have enough time or the attentional resources to do these tasks. This is both for you as well as for your computers. Okay, so from the resources perspective, temporal planning cries out for state space approaches. From the concurrency perspective, it cries out for partial order planning, plan space planning approaches. And that's an interesting thing. By the way, there is, as I mentioned last time, there is a PDDL 2.1 standard. We might actually try to throw in one more exercise for you, like you did the PDL thing, and I can also play it with the PDL 2.1 standard. So the PDL 2.1 standard looks like this. So essentially it has things like duration, and one of the things is the conditions. Since action can have a duration, then an action is like this, right? It's not just a point. So if it's a point, the preconditions are here, the effects are here, right? Okay. If it's a duration, the question is the precondition required here, required the whole time? Do you understand what I'm saying? And similarly, in terms of effects, is the effect coming at the end? Is it coming from the beginning itself? And if it is, or is it only held for a particular duration during the task? You have seen all these kinds of examples. In general, curative tasks. And so you need to be able to represent this. If you know that information, you need to be able to represent this. Okay. So then the conditions, the effect can be at start versus at end versus through overall. You can also have effects, overall effects. Okay. And preconditions in particular also can have at start and overall preconditions. Overall precondition has to hold over the entire duration of the action. Okay, and then, so for example, this one is a burned match. This is something that will come to multiple times. So let's understand this. Burning match, if you strike the match, it has a 15 units of duration, maybe seconds. Okay, and the condition is at start, you should have the match to strike it. And at start, you also have a strike pad so that you can strike it. Okay, and then the effect is at start you will have light. The moment you strike, let there be light, there will be light. Okay, at end you won't have light. At the end of this duration, you won't have light. And the crossing cellar is an extra action. This is kind of for the domain of trying to fix the fuse in a dark basement. Okay, so the crossing the cellar essentially says the duration to cross the cellar is 10 units. Let's say the condition is at start you must have the light, so that you can start walking. And over all the time you are walking, there should be light. It's a reasonable constraint, okay? And at start, you are at steps. And the thing is, effect is, because cellars typically are the basement level. So you're getting down the steps to go through the basement to go to the fuse. And typically if you don't have light, and when you're getting over the steps, you fall down. So this is all the thing that's, it's catching on to, capturing for you. So at start, you are not at steps because you already started crossing the cellar, so you're no longer at the steps. Okay, at the end, and then at the end, you are at the fuse box. So abstract all the details. The interesting is abstract all the details, and still you have this much at least you need to think about. This is what you do for going to San Francisco. At the beginning of the flight action, you are in Phoenix. The moment you are in flight, you are not in Phoenix. Technically, you are not in Phoenix. Whether if you have ever taken international flights, the moment you complete the customs and got into the immigration, got into the plane, you're no longer in US. Technically. And then when you are in the flight, you are in the no man's land or no woman's land or no people's land. And then when you drop down, then you are in a different country. That's the abstract way to think about what's happening. Of course, you can say concretely, if there's like a fire in the flight in JFK, people aren't going to say, looks like they left US, we are not going to be able to do anything. You see what I'm saying? And it's a good abstraction to think in terms of, but there will always be exceptions at the concrete level. Okay, so that's, you keep this in mind. This is a durative action, you'll keep this in mind. So, and then you can also have numeric quantities. PDL 2.1 level 3 allows you to model numeric quantities like, actual resources and so on. And it can also allow for rates of increase of resources. Again, this is interesting, even more expressive models. I mean, you can say, who is giving me this? How can I learn? Who is giving me this? It's hard to get them, I understand. But how are you going to learn it? Have you ever considered learning durative actions? The best you're doing is continuous instantaneous actions. That's what I think that you're doing. Okay, continuous dynamics instantaneous actions. So anyway, so at start here, decrease energy by this much, which is like an actual expression. The travel time and then the use rate. This is what you think. The way the fuel reduces is this way. Now, interestingly, you might say, just as you might be thinking, those of you who thought writing the PDL domain description for Block's world looks anti-AI because we should all be learning everything from scratch. And those of you who thought so would think this is even crazier. This looks like even more anti-AI because you have even more models. But then imagine NASA saying, yeah, I'm sure we'll send the rocket, it'll learn how things work. You see what I'm saying? I should show you my picture that I did when that last big thing. What was the last big thing? This thing left the solar system thing. And so, they basically had to minutely choreograph things. Learning is what you do when you haven't thought it through before and you not have enough knowledge. Okay, but learning can only be done if you can fail. Okay, NASA doesn't say we just failed in the simulator, right? So they actually will see the rocket falling down. And so the question would be, so model-based versus model-free, there is no other way than model-based for NASA. And it's like the biggest, consumer of human-written models, on which inference becomes a very hard problem. So that's planning. If I give you the model, how would you write the inference? I'm not stopping you from learning this, but just don't say, I'm learning, so I should be allowed to learn simpler models. That's not the way the world works. Okay? So if you know all this stuff, and people somehow, basically write this information down, and then, so they have rates, they can also, you can set the rate at which things are increasing, things are reducing. And one of the interesting things about rates is you can model it in such, if you model some resource level in terms of the rate, then you can allow multiple contributors for the same condition. Like, I don't know, I do very good temporal planning, it turns out, because when I go to this water and ice, where you fill up your water things, and then if people aren't, and if I'm the only guy there, I'll take like 2 taps and put it into my thing. Feel extremely good feeling. I'm a computer science guy doing optimization, instead of waiting long. That's because both of them have independent, rates. Both of them together will fill it up faster. You see what I'm saying? So this is the kind of scenario where you can have multiple contributors. You know, in the classical planning, for every condition, there is like one contributor. That's all you needed. Here you can have multiple contributors over a duration, helping you reach a resource value. This is not surprising to you because you do this all the time. You may not be doing as clever a thing as I do in the water and ice place, but you are doing something, you know, reasonably clever in your life. And so you realize that temporal planning has all this stuff. Okay, right? Then what else? So anyway, so this is the old state of the art, but that's fine. Again, as I said, modeling continuous change by discrete versus continuous effects. This was this rate information. If you hold it as a continuous effect with the rates, then the two rates can be added to get the new rate. Whereas if you say discrete effects, then basically what happens is, like if I do the tap action in the water and ice, you put the tap, the thing will be filled after some amount of time. Then I can't reason say if you put 2 taps, I'll get any faster, because there is no notion of time in the reaching the condition. Whereas if you do it as a continuous effect, then if you put the tap, the water in the thing increases at this rate, and I put 2 of them, the rate has added up, so I have faster way of increasing the rate. Okay, so that's something that you can talk about. This is what you probably are thinking about, many of you, that if you have a durative action really, and you can only think in terms of in terms of point actions, you can still do it. You can say every durative action has a start point and an end point, and you can think of that start and end points as essentially instantaneous actions. So they're connected. So the action A gets connected to 2 actions, A start and A end. And these are like parentheses. You can't write, I started the action and the plan only contains A of S, A start. That's not a valid plan. Or the plan only contains A end. That's not a valid plan. It's like parentheses. You need to have, if you start, you have to end. If you end, there should have been a start before somewhere. Okay. But if you do this, then the A start, the preconditions required there could be some preconditions that are required at the beginning of the action. That would be the preconditions for this A start action. Some preconditions that might actually be required at the very end of the action, those would be the preconditions for the A end. And any precondition that you can actually also say that the precondition is required at 17.3 units after the start. That is possible. Right? But if mostly people in period 2.1, they'll assume start, end, and overall conditions. Okay, so the precondition overall is P0. That means between AS and AE, this condition has to be held up. From a partial order planning perspective, this is like a causal link. It's just that it's not causing anything. In fact, in the refinement planning paper, I typically, the one that I kind of only mentioned in the class, and causal links are thought of in terms of interval preservation constraints. Over an interval, certain condition has to be preserved. And that's basically what it is. So if you have these 2 actions, any action that comes in between that is violating P0 would cause a conflict in partial order planning terms. Do you understand what I'm saying? So you can actually more or less use partial order planning as it exists, to solve temporal planning problems. But if it is inefficient for state space planning, for normal streets planning, it's even more inefficient for the temporal planning. It's a very flexible approach, but it's also kind of computationally inefficient. But you could do the other thing, which is you could do local search. If you ever worry about search efficiency, stop saying search, just say local search. Nobody cares about the efficiency of local search anymore. Basically, it's kind of true, because if I start with a temporal plan, right, and here's a temporal plan, and make it better, and then I start removing some of the flaws by adding more actions, or reordering actions, etc. That's like LPG. Remember the LPG that I mentioned a couple of times in the class? And the LPG representations, LPG has a temporal planning version. Well, LPGT, I think. Okay. There, you no longer are trying to say I'm doing systematic search. You're just saying I'm going to try doing some amount of it and see what I get. At that point, you don't care about talking about how inefficient versus how efficient something is. So it's a worthwhile thing to keep in mind. Yeah. So now, in general, a plan representation, an executable plan in temporal planning can't just say here are the actions in the plan. It needs to say for each action, when does it start? Right? And so it's not just the sequence. You need to do the metric time. Exactly when does it start? And if you don't, then you are saying you can do it in pretty much any time. So if there are actually, suppose you wanted to say A1 needs to come before A2, that would just be essentially, normally it's like you write it as A1 precedes A2 in classical planning. For that, it means for that constraint to be satisfied, you can start A1 today, A2 at the end of the universe. That's still satisfied. You see what I'm saying? It is coming afterwards. But many a time you say, well, after you start A1, between 3 to 15 minutes after A1's start, you should start A2. Right? This is what people say, right? When you go to your pharmacist, they'll give you like medicines, and they'll say between within an hour or two of having had your lunch, you should take this medicine. Instead of saying take this medicine after lunch. What does after lunch mean? If you were a computer scientist, usually after lunch doesn't mean immediately after lunch. Okay, so after lunch means sometime before I die, after this lunch, I take this. And so actually that helps because you probably will die without this. But the bigger point is that you might actually want to put this constraint about the start times. And these kinds of constraints are actually called temporal constraints. And it's, in fact, A1, 4, 5, A2 is shorthand for this. That means the start of A1, start of A2 minus start of A1 is between 4 and 5 units. That's the definition of this constraint. So interestingly, you can have previously in the partial order plans, you would have things like A1 is preceding A2, A3 is preceding A4. Those are the only constraints. So 0, infinity. In which case, every topological sort of this partial order is a plan. Right? Because so you can do A1, A2, A3, A4, A1, A3, A2, A4, etc. The only thing you can't do is A2, A1. Because you can't do A2 before doing A1. That's what these constraints are saying. But if you want to actually basically have these time differences between 2 points, 2 start points of the actions, then you will wind up having these kinds of constraints. And finding a topological sort is actually a way of checking if a set of ordering constraints are consistent. If you have too many orderings, like too many actions, I give you a whole bunch of partial ordering constraints. Yeah, it looks good, you might think, but it turns out that it has a circularity. Because the precedence goes transitively. So you said A1 is before A2, A2 is before A3, A3 is before A4, A4 is before A5, A4 is blah, blah, 100,000, 100,000 is before A1. It's a cycle. And you won't have a topological sum. Then you say these particular ordering constraints are infeasible. It's a cycle. Now, for temporal constraints, actually, this becomes a more interesting problem. Because if you have temporal constraints, it's not just topological sort, the numbers actually matter. So, in fact, the way you represent plans typically is like this. plans are, actions are essentially, if you think of actions in terms of the start points, then there are different time points. And these time points are connected to other time points corresponding to other actions in terms of these temporal constraints. You see what I'm saying? And these kinds of constraints are called simple temporal networks. And keeping track of the simple temporal network and checking if it is still feasible is something that a partial order planner has to do. And in general, actually, this becomes a sub-problem that is interesting in itself, in and by and of itself. Like, for example, if some humans are telling you how to do the plans, and they just have too many actions and they're giving you these arbitrary constraints of this kind. Arbitrary constraints of this kind. They don't necessarily know whether they have already made the set of simple temporal constraints be infeasible. Right? And it's basically like saying, I'll give you a whole bunch of clauses in propositional logic. Am I sure that they're satisfiable together? No, I can't. I just gave you the class constraints and you then have to figure out whether the constraints satisfy. So simple temporal networks are actually a tractable cause of constraint satisfaction problems. Where, constraint satisfaction problems, if you have heard of, basically you have variables which can take a discrete set of values and you're trying to give all the variables some values such that no constraints are violated. In the case of satisfiability, the variables are Boolean, they can take true and false as the possibilities, and you are trying to figure out a true-false assignment to all the variables such that none of the clauses are violated. That's a canonical constraint satisfaction problem. If you have a multi-valued variable, then it becomes what's called normal constraint satisfaction problem. Simple temporal networks are essentially a generalization. In general, temporal networks are essentially a generalization where the domain of the variables is a continuous quantity, not a discrete quantity. You see what I'm saying? And so, in a way, this is sort of like linear programming. Basically, these constraints will be easily solved by a linear programming solver, of course. Okay, it turns out that actually, I can spend like an entire class on just talking about simple temporal networks. There's so much that's known about them that's quite fascinating. And so people are giving these actions with, these kind of constraints with their start points, checking whether they're still feasible is actually a pretty non-trivial problem. But computationally, given a simple temporal network, checking if it is, feasible still is polynomial. Just like if I give you a partial ordering, checking if it has a topological sort is polynomial. You guys agree with that, right? However, so in fact, people like simple temporal planning that way. But in fact, one of the interesting things is that when you are trying to start with these constraints and when you actually start dealing with the conflicts in a partial order planning, you would wind up splitting these nice continuous intervals into disjunctions of intervals. So you start with something like this. Now, actually, you already noticed this. This is a disjunctive constraint. So what it's actually saying is T1 to T2 is either between 1 to 5. I mean, that means start of T2 minus start of T1 is either between 1 to 5 or between 7 to 9. You understand what I'm saying? This is called disjunctive temporal networks. If you don't have this, that means if you have only one interval as a label for each link, it's called simple temporal network. If you have more than one label, that means essentially it's a disjunctive constraint. Disjunctive temporal networks, checking the feasibility of them is not polynomial. It is NP-hard. If you are surprised, don't be, because if I tell you A1 is less than A2, A2 is less than A3, blah, 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 and that's like my partial ordering, then if I ask you to figure out, is this consistent, you can do a topological sort in polynomial. However, if I tell you that either A1 is less than A2 or A3 is less than A4 is one constraint. If you have constraints which have disjunction like this, checking if there is a valid topological sort becomes NP hard. Why did you not see this in plan space planning? Because whenever there is a disjunction, you pushed it into the search space. You see what I'm saying? So normally in plan space planning, suppose I have A1 giving P to A2 and A3 is potentially violating P. What did I do? Okay. You either, is this working? Yeah, it's working. Okay. You either put A3 before A1 in one branch, or you put A2 before A3 in another branch. One is called promotion, one is called demotion. That's bosoness. Actually, what you have is this. And so you can always take an NP-hard problem and push it into the search space and feel good about it. Because it's no longer your problem. It's somebody else's problem. It's the search space's problem. This is a classic trick everybody does. It's this business of, do you want to feel good about per node complexity, or do you want to feel good about the overall search space complexity? In fact, in a paper that I did not make you read, that we wrote called REPOP, I mentioned it in passing. REPOP essentially tries to use plan graph heuristics for plan space planning. Planning graph heuristics for plan space planning. And I talked about one part of it, where, for example, I said if you have partial order planning, it has a whole bunch of a plan space plan, partial plan. You have a bunch of open conditions going in, you act as if that is a state, even though it's not a state because the conditions are required at different points in the plan. You understand what I'm saying? Act as if it's a state, which is kind of true if you only have positive interactions, because you can make what you need in the beginning and it will hold till the time you need. And so you can actually consider the preconditioned state of the plan. That is one part that I talked about in the class. That is the other part that REPOP does, is it actually doesn't any longer throw the disjunction to the search space. It actually keeps the disjunctive constraints and does constraint propagation over there. And sometimes that's actually much faster for the overall search space. You see what I'm saying? I bring this up because in the temporal network community, people just look at the disjunctive temporal networks and act as if they have seen the devil, just because it's NP-hard. But the only reason you are not seeing the devil is because you're closing your eyes. By pushing the disjunction to the search space, then you'll get samples into temporal. In fact, you know that if you have a causal link and and there's a flaw, causal link violation, you get a disjunctive constraint. Unless you push it into the search space, it is a disjunctive constraint. If you can get it here, don't you think you will get disjunctive interval constraints on the timed actions? Of course you do. Right? Because what happens there is, this would be an interval, this would be an interval, you know the start points of each of these intervals, and you have to say either this guy comes before the start point of this guy, enough such that it will be done before A1, or it comes after the end point of it. That's a disjunctive interval constraint. Okay. So that's one of the side notes of thinking about partial order plans. If you have partial order plans, you have to actually maintain simple temporal networks And temporal networks you have two types of temporal networks, disjunctive as well as simple temporal networks. It's like a whole entire area in this. And people who are in temporal planning, they assume that maybe humans might give me actions, but they might give me these kinds of constraints, and I need to figure out dispatch policies. That is, if I have a large enough plan with a huge number of actions with these kinds of constraints, then I'm asking, what should I be doing next? It's not as simple, because the plan is actually a partially ordered plan with these continuous quantities. And so in essence, you are trying to figure out and solve the disjunctive temporal network problem every time you're trying to do this dispatch. And if you want to do it fast, there are all sorts of interesting heuristic approaches how to deal with the disjunction. Okay, there's a ton of this kind of thing. Okay, so if you're trying to solve temporal planning problems, the way they typically are specified is that you essentially have goals are specified in terms of not just the goals, but the goals and the time point by which the goal should be satisfied. And you can also have goals that should be satisfied over an entire interval. That means that the entire interval, the goal should be true. So it's either point goals or the interval goals, which correspond to point preconditions, which are sort of the dual of point preconditions and the interval preconditions. And also point effects and interval effects. Okay. So then basically you can also have these goals have either a point, or you can also say it's a deadline. That means as long as it is done by this time, then you're done. And deadline goals are quite useful because that's more or less how, even though there is a feasible plan for your MS program of study that is strictly sequential, you tend to have this nonsense thing called life, which poses deadlines, saying I would like to be done before 65, with my bachelor's program. And so that's a strong deadline. And so you kind of might say, if I do it in a sequential way, it might take too long. So I have to parallelize some of the courses. Okay, so deadline goals actually push parallelism, but it's a weaker kind of required parallelism. If the deadlines are relaxed, you can still do it sequentially. Okay. Now, if you have this normally, what is a plan quality measure? Previously, we talked about the number of actions, the cumulative cost of the actions. Those are the kinds of things. But now that there's time in thing, you can talk about all sorts of other things. You can talk about make span from the beginning to the end. How much time do you take for the plan to be done? Okay. Slack, which is the difference between the deadline for a goal and by the time by which the plan achieves it. And you might want to minimize the slack, you might want to maximize the slack. And as I mentioned, slack is useful for robustness. If things go wrong, it's the slack that you can use to still reuse the plan. Okay. And of course, you can also still use cost, which is the sum of all actions. At a minimum, make span and cost are two things that temporal plans have to deal with. And in general, this is sort of the fundamental trade-off in temporal planning. Okay, so typically the cost and time are the fundamental trade-off in temporal planning. So for example, if you're buying tickets to go to some faraway place, right? Then basically I can do this 15 flight change ticket. That is $1 less than this other ticket that is only 14 flight changes. That would be, $10,000 less than linear air taxi, which will take me from here to wherever I want. I don't know whether you guys get this. When I'm looking for flights on kayak, I think they kind of realize that I have some money or something. They show me linear air taxi to India, apparently. So I think that thing will just fall in the middle of the ocean. But so this linear air taxi is like an air taxi. There are services which, if you don't feel like standing in line at Sky Harbor Airport, this air taxi will take you to LA and places like that. It's only $2,500. You can afford it, right? But anyway, so the question is why, if I see, this is actually one of the things that I use in that reference thing. If I see a bunch of graduate students going to conferences, behavior based, I would see that they like to travel late nights and they try to get as many flight changes as possible. It's true, right? So I would think looks like that's what you're doing. If behavior is what preference is, then oh, what's happening with this? Is there a better battery? Is there somebody else has a iPad battery? Because this one is not good enough. So, iPad charger.
Is it USB-C?
No, this is just I just a USB with
Is it same as the iPhone charger?
yeah, I think no, yeah, the charger is probably. I think it may not be enough, but I'll try. Okay, let's see. That thing is bad. So this is probably slightly better.
Need something beefier, I have this.
Oh, that's much better. It is. Yeah, that is that.
That's, yeah.
MacBook.
Yeah, that's great. Yeah, we can be here today. And you have him to thank for. What the heck is that? Good. Okay, fine. And this is somebody's. Okay. So what was I about to say? Some nice example. Air taxi. So if I see graduate students' plans, from their behavior, it seems like they like overnight flights. They like multiple stops. If you like something else, why aren't you doing that? Well, there is a little thing called money, and you apparently don't seem to have it. That's why you do this, right? So this is a classic example of preferences obfuscated by feasibility constraints. You see what I'm saying? The only way I know that is your true preference is there is no other resource constraint and you're still doing it. Then I know. But anyway, coming back to this, plan quality measures, typically at least you have make, span, and cost, because of which essentially optimizing temporal planning is often a multi-objective optimization problem. And you have to talk about things like Pareto front, which I talked about in the very beginning of the class. Because I will give you two flight plans to go to, let's say, Pittsburgh. One basically takes 5 hours and costs $400, and other $900, and the other takes 16 hours and costs $700. They are in essence incomparable. I know what I will take, but I know what I hope my students will take too, right? So the question basically is that it's a multi-objective optimization problem, and so heuristics for temporal planning have to take multiple objectives into consideration. Actually, the work on SAPA was its biggest contribution was that really in terms of dealing with the multi-objective heuristics. But we will not even get into that. Okay, so looking into STRIPS actions from PDL 2.1 vantage point, you can think of non-jurative actions either as instantaneous actions, which basically makes them not have any physical semantics because there's nothing in the world is instantaneous, seriously. But you can also say they are epsilon duration with only overall preconditions and at-end post conditions. So that means actually STRIPS actions are like this, very thin actions. The preconditions must hold over the entire duration, and the effects will hold only at the end. And there is a very interesting concept that's useful called temporal gap. Temporal gap is essentially, you would say that a domain model has a temporal gap if an action has a temporal gap. And you will say an action has a temporal gap if there is a point where the precondition is needed and a different point where the effects are. You would say there are no temporal gap if there at least exists one point where all the preconditions are needed and all the effects are needed. Do you understand what I just said? Okay, so for example, an action like this, I need the precondition here, P1, I will give the effect here, E1, that has a temporal gap. Whereas an action like this, where I need the precondition, the entire place, and effect is given at the end, has no temporal gap because there exists at least one point where all the preconditions are required and all the effects are given. You understood that, right? It's very interesting because if a domain model has no temporal gap, in essence, it's a strips domain model. Because that you should have realized it by now, because I just said I can think of strips as epsilon duration with overall preconditions and at and post conditions. And strips can be solved with just sequential plans. The parallelism is only luxury, it's just syntactic sugar, right? Which means that in fact, if you have any actions, even if they are not epsilon thin, it's not epsilon that matters. It is that there's a point where all the preconditions are required and all the effects are. Then any domain where there is no temporal gap will essentially not require concurrency. That means you would not need concurrent plans for feasibility. You only require concurrent plans for efficiency. Okay, you understand what I'm saying? Now, I ask now a question which anybody answers, I would think this course has been amazingly successful. Whoever answers it will basically just, you can tell me what grade you want. Okay. Which is, what does this remind you? What does this remind you? We talked about something very similar. The entire damn point of this class is ignore syntax. Metaphors and analogs exist in higher plane. Okay, you can't just say, well, I know this cannot be done in temporal planning, but I'm talking about a different kind of a plan. The issue is everything is connected at certain levels. We did talk about something like temporal gaps somewhere. Yeah.
Options?
No.
No.
Options is actually messed up. In fact, you can ask yourself, you can ask them why exactly are many of these problems not there in options? Because options essentially, I mean, we didn't talk about temporal gap there. Essentially, options are strips plans, strips policies, and only the people taking it for credit, because people not taking it for credit, how does it matter? Anybody going once? Yes.
Upward refinement in like hierarchical planning, because
think a little more. You're warm, surprisingly warm. So think of what he's thinking. He's thinking of hierarchical task network planning. Did you even think we have any connection to hierarchical task network planning? I've said the topic changed, so I should change my mind. I shouldn't see any connections between what happened in the previous topic and this topic. That's one hope that's one thing that I hope you won't do in life. Everything is connected to everything. And you need to allow for those insights to come. Okay. You're very close, Lucas. You almost can tell me your grade if you want. Somebody else who want to?
Escape action.
What?
Escape actions.
What happened?
Escape or micro actions.
No. No. So shall I tell you? Okay. Yeah.
This kind of guess. Is it belief states in POMDB?
No. I already said he's close. So you're going far away from him. Be like Lucas, but only better. So, that's what my point was. Remember, there was a problem we talked about in hierarchical task network plans where at the high level, there is a causal conflict that cannot, there's a pair of causal conflicts that cannot be resolved. So you would like to kill the plan there because the causal conflict can be resolved. But then when you expand it, you'll realize that A and each of these actions become multiple actions at the lower level. So the conflict now suddenly has a gap because of which it can get resolved. HTN reductions provide temporal gap over instantaneous actions, because of which something that you think is actually infeasible at the hierarchical level is actually feasible. So what was the solution we came up with for that? Unique main subaction restriction, where we said by fiat that we should have HTMs such that if a task is having preconditions and effects at the high level, then whatever reduction you do, there exists a unique main subaction which takes all the preconditions, gives all the effects. I went on and on and on and on and on about the assets and the debts of your parents. And I said that, if there exists one kid who has to get all the debts as well as the assets, that would be the unique main subaction. And I said, if that is the case, then if you have a conflict that cannot be resolved upstairs, it cannot be resolved downstairs. Very interesting connection. Actually, it's basically it's not an accidental connection, because hierarchical plans have temporal scope. Hierarchical plans have temporal abstraction. Except they are not interesting. They're one type of temporal abstraction. They have more. I mean, one point became multiple points, but you still don't talk about real time. Options is the same nonsense. One point becomes multiple points, but we don't talk about the action time. You understand what I'm saying? If you add multiple epsilons, it's still epsilon. That's how calculus works. Multiple infinities is still infinity. Right? So basically, options and HTNs, etc., are four persons' way of doing time. And so essentially, it doesn't require concurrency like ever. But in the case of HTN, actually, if you don't put the unique main subaction, you will have some of these problems, such as, if you don't have unique subaction, main subaction restriction, then what you thought is a dead plan is actually living again downstairs. And in essence, what you did is you ensured that there's no temporal gap by requiring, by fiat, that all the debts and the assets go to the same point. Remember, action is a point in all these formalisms. Temporal planning is the first time where action actually has a duration. So it's not enough to just say the action, one action in the temporal reduction gets all the preconditions, all the effects. So you have to say it will not only get it, but all of them will be required at the end point and will be, and the effects will also be given. So that means there should be existing one single point which would have all the required things. And that will, if you do that, there is no temporal gap. And if there is no temporal gap, strips can solve temporal planning problems as far as theory is concerned. The rest is just efficiency, post hoc efficiency. You come up with a plan and you sort of improve it by squishing actions in parallel. Is what I'm saying? So two more things. I may actually have to come back to this a little bit later again. This is a temporal gap thing. The 2 points I want to make before, actually this is actually beautiful. Yeah, so one of the temporal gap thing makes a difference because essentially if there are domains where none of the actions have temporal gap, that means duration is a syntactic sugar. How many of you have heard of this word syntactic sugar? Yeah, so it's a good way to get papers. You take a problem that has been solved and then just say, well, they solved it, they wrote the paper in a 2-column format, I write it in the single column format. Not too many people will understand. So you should come up with other kinds of syntactic sugar, such as they do it in planning, I do it in RL. That I'm hoping you would avoid doing. Okay, so syntactic sugar basically means there is really no difference in the in the problem itself. You just added some extraneous details which don't change the underlying nature of the problem. Okay, and so if you have actions with no temporal gap, then the best way to think of them is all of these actions are actually the stars is the point in each action that actually matters. Because that's where all the preconditions hold, all the effects are given. You see what I'm saying? So the duration is just syntactic sugar. Whether or not you can solve the problem is based on the points. And then you do optimization in terms of the duration. So that's actually what this particular thing basically says, that if you have actions with no temporal gap, then the best way is to think of them as point actions with a property called duration. Okay, and solve the action, the plan at the point action level. When you solve the plan at the point action level, I'm sorry, where did I go? When I solve the plan at the point action level, what did it do? Yeah, I meant get basically a sequential plan, something like this, which is a purely sequential plan. And then in the post-processing stage, I just essentially condense to minimize the next time. It became a post-process. You can always take a plan generated by state space planner and make it more parallel. I hope you guys understand. Right? If you take something like strips plan, I mean, like a progression planner generates a plan that is prefix, right? After you get the plan, you can ask yourself, yes, you found it that way. Is there some opportunity for parallelization? Well, you reprove the correctness of this plan in causal links. And if you reprove the correctness of the plan in the causal links, then you can easily see what orderings are required, what are not required. You can remove the non-required orderings. You parallelize the plan. This essentially is a confusion that lots and lots of people didn't realize for the longest time. Because essentially in one case, that's why in classical planning, ultimately you never really have to search in anything other than the space of operator sequences. Because the final solution is an operator sequence. And if you have a partially ordered plan, that basically is just saying there are multiple such sequences that this partially ordered plan represents. All of them are fine. It gives you some kind of an ordering slack. You see what I'm saying? So if you have actions without temporal gap, then in essence you can do state space planning. Simple state space planning followed by condensation of the thing, and that is actually a pretty simple approach, and it works well. If you, on the other hand, have actions with temporal gap, and this is the ending more or less of this class, that is the crossing cellar problem is one such. Okay, where there is no single point where all the preconditions are required and all the effects are given. Because of which you can't actually cross the cellar without the match being lit at the time when you are crossing. You can't actually come up with a sequential plan for crossing cellar and then parallelize it. You guys understand that? It's important because if you're only ever searching in the space of sequential plans, then this guy's solution won't even appear. If it doesn't appear, optimizing it is not an option. You see what I'm saying? Okay. So essentially, in the case of cross-cellar problem, essentially, most state space approaches will fail. Actually, all state space approaches will fail because they'll only be complete for actions without temporal gaps. Okay, and the plan sort of looks more like this. You burn a match, and while the match is burning, you have to cross the cells. There is not a single sequential version of this. And this is clear for you because essentially, which action here has a temporal gap? This action has a temporal gap because there are, let's see, I think it's written there are some effects here and some effects here. First of all, if you have effects in 2 different points, then you already have a temporal gap. Right? That basically means you can't think of this action as just a point with an extra, I mean, it's like basically, for some strange reason, it's like it's an action masquerading as a derivative action. It just put on a bit of heft. It's really a fixed action with heft. Okay. So it turns out that partial planning search can handle this, even this sort of a situation. And in fact, the very first kinds of planners which solve this problem is a planner called Zeno, which is just a direct extension of one of the first planners. Actually, it's not the very first planner, but it's a direct extension of our plan space planning. And it's just very simple to extend. It's actually quite cute to do, and they do all these things like disjunctive constraints, etc., throwing in, etc. But search space is extremely big. The one thing that this is Scott Penberthy and Dan Weld. The one thing that they didn't know at that time, and people didn't know in general at that time in computer science, is when in doubt, say I'm doing local search, and nobody will question about your efficiency. I mean, as much as I sound cynical, these are actually useful pieces of advice. If you want to write papers, you can do this. Okay, because if you do local search, you can't say search space size matters. I mean, how the heck is gradient descent ever going to make sense if you think in terms of anything other than local search? In general, the intro to AI combinatorial search tends to think in terms of systematic search. Computer science in general tends to think in terms of systematic search, because systematic search, you can prove theorems. Local search, you hope for the best. And you say, my paper seems to do better than other people's paper. That's it. Okay. I mean, sometimes local search is the only thing. In continuous space, it's not at all clear what you can do in other than local search. But once you are into the local search, you could do that for plan space plans. LPG temp does that. And then you no longer have to say some more plan that I am stuck between doing the right thing versus doing the fast thing. But more importantly, I also want you to understand that this entire community of reasonably smart people were essentially lulled into this stupor that somehow we didn't expect state space planners to do at all, but temporal planning. In fact, I'll tell you this and then end. Okay. So the version that I told you, which is just solve the problem as if this is a sequential problem and then parallelize it, you won't get a paper. Right? Because you're admitting that they're not really, there's no duration. They're actually temporal plans. I mean, the instantaneous actions with heft. So you could do something a lot more complicated. In fact, you can do this idea called generate the state, the parallel plan up front such that it's optimal. There's no post-processing. So in fact, in the context of post-processing, one of the issues is depending on the sequential plan you got, the most optimal make-span optimization version of that may not be the optimal make-span plan. So there may be 3 or 4 feasible sequential plans. And you have to see which feasible sequential plan leads to the globally the lowest make-span. Right? This is sort of like gradient descent, where like multiple inflection point, multiple points are there, stationary points are there. Which one has really the lowest value for the function? That requires more global search. There is no hand waving there. Okay. So instead, what you could do is instead of doing this post-processing, you can say, I will try to develop a state space planning idea, which I will go back again and talk more slowly next time. But I want you to think about it. Where, remember, we normally used to start with the initial state, put in action, next state, put in action, next state, put in action, next state. That's how state space planning, forward state space planning works. I would argue that what you are doing is lengthening the plan. Right? But you can actually say, when I'm at a point here, this is my start point, and I have an action here, I already put. I don't necessarily have to, I have to actually say, I have two choices. One is, what is my next point where I'm putting the actions? I can keep the clock here and put more actions, and then suddenly I have concurrency. Or I can advance the clock and then start putting actions. You can think of not advancing the clock and putting new actions into the plan as a fattening operation. It fattens the plan, makes it more concurrent. But of course, you can't do things concurrently if they are actually getting into each other's nerves. Like such as, these concurrent actions should not have any kind of conflicts, such as one's effects violates other guy's preconditions, etc. The whole stuff. So you could either keep the clock where it is and put in action that doesn't interfere with the current set of actions in that time point, or you extend the clock. So take the clock, that's the internal clock, okay, and then start putting actions there. If you do search like this, then you can essentially get optimal make-span solutions without any post-processing. And the planner called SAPA, which my student Mindo did back in 2001, essentially got that. And I'll actually walk you through this. It's very interesting paper, very interesting, idea, but the idea ultimately becomes, instead of just extending the clock, which is what normal forward state space search does, it says either keep the clock and fatten it, or push the clock and lengthen the plan. And it turns out it will be actually a generalization of normal forward state space plan. And this will actually get you the optimal concurrent plans in one fell swoop. And so Min did this, and he also actually came up with a multi-objective heuristic based on planning graph. And there's a SAPA paper in it. I'll talk to you slowly later on. We did this. I'm not just talking about other people who did this. I did this, and it turns out, since Rao did it, does this also have the problem with temporal gap? Yeah, of course. We did it, and in fact, we were winning competitions. Everybody else, because we were winning competitions, other people did the same kind of temporal planning. In fact, this is called, we even made a nice name, or somebody made a nice name, whatever. Decision epoch planning. The decision epoch is the clock where it is. In that epoch, you can add more actions. You extend the clock, you can add more actions. You can extend the clock, you can add more actions. The dirty secret is the clock is normally extended only to the end of an action. If you try to extend it continuously, it becomes just as hard. In fact, a dumber version of doing plan space planning. Instead, what you do is, if I have to extend, I will extend it to the end of whoever is the longest, one of the actions at least. And so that there will be new concurrencies from then on. It worked quite well. And it was winning competitions. The reason it was winning competitions is because it turns out that decision epoch planning does not solve problems which require concurrency. Okay. And so, in fact, I don't know whether I have this here. Yeah. So this is, let me just. So the matches problem, basically, this was a 2007 paper by Bill Cushing, guys. Some of my students know, we heard of the name. So I actually have a little video snippet of it, him presenting this in Hyderabad, and he's a very nice, smart guy. Probably one of the smartest students I work with. But he essentially takes the fuse problem and tries to show that essentially the only epochs that decision epoch planning will consider is either starting the next action here, starting the next action after this action, or starting the first action after this. Those are the only plans in the state space. And you see, none of them will work. But just this simple. The strange part is this was the canonical example in the PDL 2.1 manual. This is how communities can collectively close their eyes. And it's nothing wrong with planning community. Every community has this problem. That's why it's important to understand. Okay. So it turns out that none of these will work. No epoch is available for middle of nowhere because the only reasonable epoch station epoch planning will consider for efficiency's sake is the beginning or end of action. And so, there was like a big war movement basically because the things that are winning competitions are solving problems that the competition doesn't even capture, even though its title says it captures. These are not temporal planning problems at all. There are fake temporal planning problems, which actually could have been solved by sequential planners. And so, to some extent, it's actually useful to understand that the temporal is simple. It's much better to just do classical plus scheduling. And otherwise, you essentially do what's called what's basically the plan space planning, which is you consider each action to be 2 points with the causal dependencies and do plan space planning. I'll send you this paper called, actually the title of that paper is When is Temporal Planning Temporal? It's not really temporal if it can be, you can ignore that temporal. I mean, if you're saying I'm good for this, and it turns out that's just a secondary property, then you're not really good for that. Okay, and so that's sort of a thing. And it's kind of useful to think about this sort of a thing because this is how collectively communities can lose track. And benchmark-driven research in general has this huge problem. Let me leave you with this very last parting thought, which is, I mentioned this already. All the preference learning from trajectories people assume that there is a reward function on the underlying state space. Not trajectories, but the states. But trajectory preferences cannot always be translated into state reward functions. What was the example? Partial satisfaction planning. You could not actually convert partial satisfaction planning into an MVP without introducing an extra variable called done, doubling the state space, and then make the reward Markovian. Because if your reward is actually only dependent on state, it becomes what's called Markovian reward. Trajectory preferences are non-Markovian rewards. In general, are non-Markovian rewards. Non-Markovian reward can be made Markovian reward if you blow up the state space. The paper that you read of Paul Cristiano, does it say it increases the state space size? No. Did you see if this is a problem? No. Did you not hear that there is something called non-Markovian reward? Of course you did. I was going on and on about it a couple of classes back. This is how we can all essentially be collectively miss some points. Once you admit this inconsistency, you can at least understand why is it working. It turns out that some non-Markovian rewards can possibly only learn those non-Markovian rewards on trajectories that are actually expressible as Markovian rewards in the current state space. This is a theorem. I don't even need to prove it because that's what the paper says. And yet, trajectory constraints are not Markovian. I mean, preferences on trajectories are not Markovian at all. So, thus goes research. Okay. The point is always be skeptical about what you read. That's important. Okay. Thank you very much. Thanks for the extra time. You should take your, thank you for
That's
saying
actually
it.
the recommended way of doing this.
Yeah. Okay, I might.
Did not say that. Oh.
I drove.
That's that.
Oh.
That's what you're at home right now, right?
Yeah, yeah. Take care of me.
Have a good one.